All right, welcome to 4G.
Yay.
Power and capacitors continued. But let's go back to power and dBs and capacitance. So somebody want to, now I'm going to cheat. You've had a chance to see that. Somebody want to read off what they are? Not read it off, but tell me what they are.
Micro, 1 to the, or 1 million. Micro, 1 million.
No,
Millie's next.
no, there's 1,000.
1,000.
One,
What's the next one? 1,000. 100,000.
no, you said 1,000.
It's 10 to the
It's
3.
1,000th.
Oh, yes, of course,
I
sorry.
didn't enunciate.
Yeah, 1,000.
Yeah, and then what's the next one?
Okay,
K, which is for what?
100. No, sorry, K is 1,000
1,000.
Yeah, but what does the K stand for?
kilo.
Kilo, right? And then what's the next one?
100.
Mega.
Mega.
Omega for OPM1.
Are you looking at your notes?
Well, yes. That's because that was one of your suggestions for learning.
Absolutely, good for you. Mega, like we'd say mega ohms. Or,
Megavolts, so
mega-
that's a million.
Megavolts, that's a million. And megohms is a real common thing. Megavolts is not common. But anyway,
Megavolts. The volts.
memorize this. This is something you need to know. You need to know it by heart. So let's keep working on that. And power, and the
Yeah.
one that I'm concerned here for is,
P equals E squared over R.
look at that. John said that he looked at the sky. He didn't even look at his computer. So
No, I
All right.
forget. Why is that the one that's more important?
because what we're going to do here very shortly is we're going to check the power of a radio.
Oh, I see. Okay.
And that's the formula that we use to do it. So transmitter power test. Now this is my oscilloscope. It's a digital oscilloscope. But I wanted to show you this. This is my oscilloscope. It's a digitizing scope. And this is its normal mode, but so that you can see the screen well. This red line is set at 0 volts. And what I'm going to do here is I'm going to transmit into a dummy load, which folks, I'm stuck. If I turn on the light back here, it reflects right here on the screen. And then we can't see the screen. I wanted to show you what's going on over here, but anyway, I have a 100-watt transmitter hooked up to a dummy load, and I have it hooked up to this oscilloscope. So when I click transmit, you can see me starting to show up. Now this radio is on single sideband, and I'm holding the microphone down by my belly. Now this is the normal mode that it would be in. And you can see there are, hello, hello. You can see there are peaks. So you don't look at this stuff down here, but you look at the peaks, which are right up here. Now, you may not be able to see this where you are, but this is 50 volts per division. This is 0 volts. This is plus 50, plus 100, minus 50, minus 100. So if we're looking at this, and then we go up to here and down to here, now look at this. Notice it's going from up here to down here. That is peak to peak, 200 volts. but all we want is the peak. So here we go. We're going from 0 up, and even though I slightly go over once in a while, we're just going to call it 100 volts to make things easy to work. So the FCC decided they would use this in order for us to be able to figure out what our peak envelope power is. Now, do you remember me talking about RMS?
Yeah.
Yeah, we multiply the peak by 0.707. So what we do here is we take this peak, which we can see real easy on the oscilloscope. And that's how I do it every time I measure. I just go on like that. So,
And what does that give us? Peak times 7.707?
the peak envelope power,
Oh, okay, yes, of course.
or the RMS of the peak envelope power, excuse me. Peak envelope, excuse me, voltage. This is my oscilloscope. This is 0 volts here. So when I speak into the radio, which is hooked up to a 50 ohm load, and we're looking at that with the probe of the oscilloscope. So as I talk, what you're seeing is going from 0 to peak. Hello. So we're going from peak to peak. Well, what we want to know is what the peak is, which goes from 0, which is right here, up to here. Yeah, you might notice sometimes it goes slightly over and I will often count that. But for now, I'm just going to use the 100 volts, so it's a lot easier for us to use. Okay, somebody tell me what the formula is for power.
Did you pin it?
No, I did not.
E squared over R.
E squared over R. And that equals what?
Power.
Power equals E squared over R. So what do we know about E?
It's 100.
It's 100 volts. But 100 volts what?
Peak.
Peak. Now I used to, and I did this for a while, and I was rather confused because everything I tested turned out 200 volts, 200 watts. But the FCC said they want the RMS value of this 100 volts peak. So we multiply this times 0.707, which ends up being 70.7 volts. So I'm going to take that. Use my calculator. Whatever voltage we come up with, but so let's take 100 times 0.707, which will give us the RMS value, and that equals 70.7. And then I take that and I square it. And there's the square on my calculator. Press that, and I get 49.98. Then I divide that by the resistance. And we have a dummy load at 50 ohms. 50. And that equals 99.96 or 100 watts. Did everybody see how that is done? John, you do this?
I have a
I heard a question.
Joe.
Yes,
The 0.707, is that a constant?
it is a constant, yes.
And that's so for no matter the frequency, no matter the radio, it's 0.707 times the peak voltage.
Yeah, that if you have an AC signal, a sine wave AC signal, and you multiply the peak voltage of that by 0.707, that will give you the RMS value, which is root mean square. And that is, if you took the AC and you converted it directly to DC, that is the amount of power that it would be. So if you had 170 volts, it would come out to be 115 volts DC or RMS. And when we talk about 120 volts coming out of our outlet in our house, that's RMS voltage. You'll notice that some of the meters, if you were shopping for them, said RMS meter. That's because they calculate true RMS. Any more questions?
Thank you, Joe. That answered mine.
Oh, good, good, thank you.
So, yeah, I have a question. So the RMS is qualifying the voltage. Is that right?
I would say that is correct. What it's doing is it's taking something that's odd shaped, but most of our AC signals are not what you saw on the screen because that was voice.
Mhm.
But if you transmit CW, it will be a pure sine wave. And a pure sine wave will convert to RMS. And in fact, in this lesson, we are going to study that in great detail.
Okay.
So any more
So-
questions?
Yeah, I have one more.
Yes.
So when we go back to our basic formula that P equals E squared over R, is it always E sub RMS?
No.
So see, that's where I got lost. So how did we get from just E squared to,
Unfortunately, the FCC arbitrarily decided this is the way it would be done.
oh, okay, okay. So they're just saying substitute E for RMS.
Yeah, if E were a DC voltage,
Yeah.
you would use it directly as it is.
Mhm.
But if it's AC, you want to know what its actual value is, how much heat it will produce if put into, say, a pure resistance.
Oh, I see, okay. That makes sense.
Yeah, and we'll answer that question in a lot more detail here in a little bit. So let's
Well,
Go
another
ahead.
thing,
let's
if I might, just to ease some folks' mind there, Joe said that he adjusted his transmitter. He just turns his the knob or on his transmitter to put out 100 watts. It's a 100-watt transmitter. He adjusted it to 100 watts, and then we went ahead and saw the sine wave at that 100-watt that transmitter at 100 watts, and gave, and it was 100 volts. 100 volts times 0.7, and then we did the equation, and we came out to darn near 100 watts, 99.97. So, so you can tell then that, by golly, that that transmitter is set up properly, and it's putting out what it says it can put out. When you turn the knob to 100 watts on the transmitter, by golly, it actually puts out 100 watts. And
Right.
the reason I might mention that this is so important is that when you all are, as a ham operator, sooner or later, let me tell you, you're going to be wondering if you're actually putting out X amount of power with your piece of equipment. because you don't know if something is broken or if it actually is working or not, because maybe nobody's answering you. So at any rate, this is how you find that out, and it's really important, and it's fairly easy to do.
Yeah, this is one of the most basic tests that you give a radio. When you turn it on, see if it's receiving, you check its transmit power. And what's nice about this is you can just go from band to band to band and speak into the microphone and see how much it puts out. And if it's putting out 100 watts all the way across, you're in good shape. I found that some of the really old radios, when they hit 10 meters, they might drop a little bit in power. Might drop down to like 80 watts or so. But that's back in the day when the transistors would not make it. So let's
So, oh, sorry, Joe, can I do another question?
yes.
So last week, we looked at the transmit power using this, I don't know what it was called, but it had the decibels, it had the S, and it had the SWR. Right? What is that little box called?
The SWR meter, is that what it was?
I don't know.
Oh, here, just hang on a second. I think I want to review and maybe you'll tell me which one you're talking about.
Okay, so my question is, so Scott was saying, so one of the things we'll want to do is determine if the transmitter is working, and we do that by looking at the transmit power. But tonight we did it using the oscilloscope. And I think last week we did it using this other thing.
Oh, no.
Does anybody know what she's talking about?
Yeah, but these equations here aren't really used. We don't at least I don't use these to find out what power my transmitter is putting out.
No, this is I'm getting ready to go on to DB here. So,
Okay, well, go on.
but we'll
I'll-
farther in we'll do this. But let's hold your question. Okay, DB, this is something, when we were talking about this before, I was talking about going from 100 watts down to 5 watts, going from what we call barefoot at 100 watts down to QRP, which is low power, which is typically 5 watts. That's a 13 dB in power loss. And so what would that make a difference on your VU meter? And I had to do considerable amount of research. I did misinform you. So anyway, but I'm going to explain that now, I hope. But speaking about dB, let's just talk about the different kinds of dB. This is one of the important ones, antenna specifications. Here's a Yagi antenna. This one happens to be a 220 megahertz antenna. Here is the gain of the antenna compared to frequency down here, 220 megahertz, which is almost 10 dB. These are dB. 0 would be 0 watts output, or excuse me, if you had a dipole, this is how much gain over a dipole. And this here is an illustration of how the antenna takes the signal and reshapes its directivity. So in front of the antenna, this would be 0 dB. But according to this, at that point, that's a 10 dB gain about. Back here, if you go at this point here, this is off the back of the antenna, straight back. Back here, you take that point here and you come on around, and that's minus 20 dB. So you get much more signal from the front of the antenna than you do from the back. And you see these deep notches here? If you had somebody who was really interfering with you, if you turned your antenna just so that he was coming off this notch here,
Mhm.
even if somebody were coming from this direction here, you could tune that guy out and actually be able to receive this guy here, much improving your signal. Because sometimes people are just on the same frequency and they don't even know it because they're on opposite ends of the country. And that happens. And you're in a spot where you can hear them both. You know, it's just one of the things of amateur radio. So that is one important thing to understanding about dB and gain. These are, by the way, called side lobes, and they get a little bit of reception or transmission there, and these also here off the back of the antenna. But most of your signal, when you transmit, goes that way, out the front of the antenna, out this direction.
So, Joe, I'm sorry, so on the directional plot, what are those numbers that are going around the circumference?
That's degrees.
Degrees?
0 degrees, 90 degrees, minus 90, and 180. 180 is the opposite direction.
Oh, I see.
Good question.
So you're up looking down over the.
Yeah, you're looking down over the top of the antenna. And then these figures are here are in dB, -4, -8, -12, and so on, down to -28 dB. And you can see these notches really knock out the signal.
So those dB gradations
Here.
going down would be the same as in this gain response table? I mean,
No, they're these excuse me, dBs are dBs.
yeah,
It's a gain reference. This is a gain from off of a in the forward direction off of a dipole antenna. This is the gain.
of the other antenna.
Yeah,
Of
but
the-
this at this
of-
point, this is considered 0 dB, which by this plot here is almost 10 dB over a dipole. But we're comparing the whole antenna to itself. In this diagram here, we're talking about a dipole. See this beam right here?
Yeah,
That's the driven element, and that is a dipole. So you put a reflector back here, which sends a signal that direction. And then these are directors, and they're placed so that they will cause the signal to go that way.
so I understand that. What I don't get is how do you get, I mean, how do you map the 0 point on the directional plot to this gain response table? You say it's 10 dB, but how do you know that?
I know that this point right here
Yeah.
is the maximum gain of the antenna.
Oh, and then you look over here at this other chart and you see the maximum gain is 10 dB.
Correct.
Okay.
Okay.
Yeah.
And by the way, we will be studying this in great detail much farther into the course. But I tell you these things so that when you get there, you will already have some idea of what we're talking about. Which it's an important thing to learn. Now, this is one other one, and this is one that you will need to learn to deal with. Now, these are different kinds of coax. And I've got a bunch of coax here that I'm going to show you in just a moment. But before we do, let's look at RG8 antenna, and let's look at 150 megahertz, which is real close to what we work at 146, 147 megahertz for our repeaters, right? So if we come down here, we go to RG8, which is the old standard, that's 2.4 dB of loss in 100 feet. So if you cut that and it was only 50 feet long, it would only be 1.2 dB loss, which is very little loss.
Where did you get the 50 feet?
I do, this is per 100 feet.
Oh, the cable.
Attenuation in
per-
dB per 100 feet. So if you got 100 feet of cable, you're going to lose 2.4 dB.
So the word attenuation equates to loss.
Correct. Attenuation means loss. Now, I want you to look at RG58. Notice that at 150 megahertz at 100 feet, it's 6.1 dB. That cuts your power. If you were putting out 100 watts, which is not likely on that frequency, you would be cut first at 3 dB would be down to 50 watts, and 3 more dB would be down to 25 watts.
Mhm.
So if you had a typical 30 watt transmitter, you would be cut down to 15, and then you would be cut down to 7.5 watts, which is hardly more than a handheld.
Now, the cable that we're talking about is between what two things?
Between your transmitter and the antenna.
Okay.
So-
Well, this is probably important to me.
It is very important to you. And when a lot of people are just not aware of these things and how much they lose when they do these things. Now, if you're
So
the
if I
typical,
knew how many feet I needed to have between my transmitter and my antenna, I could decide what kind of cable to use.
correct.
Yeah, okay.
And it depends. I mean, if you're in an area where you're only 5 miles from the repeater and you got a direct line side of it, you could use 200 feet of RG58, which would be a 12 dB loss, and it wouldn't make any difference because you're right there and you can get the signal. But if you happen to be in
Rose Lodge.
Rose Lodge, that's a good one.
Don, yeah.
Yeah, if you're done and you're running that, you're not going to hit the repeater. You're not going to be able to get enough signal into the repeater to get it to work. So let me show you. Okay, here are a bunch of coaxes. Now remember, folks, when we get to transmission lines, we will be going into this in detail, but these are all coax. Now, who wants to tell me which one of these is the RG58?
The big one, or the small one.
Second one from the left.
The yellow one.
This one. See this little one here? You can see it's a small thing. If we look, it says RG58 right there. And if you're only going 10 feet and you got 100 watts or less, it's no problem because in 10 feet, you're going to have very, very little loss. And most of the time, that's not going to be significant. So very often, your antennas that are on the roof of your car use RG58. And hopefully they're using a high quality RG58, which this one happens to be. I purchased this. Be careful, there's some really cheap stuff out there. Then we go to this one. Actually, these two here. I have this one because it says RG8 focus, RG8X. This happens to be marine wire. The cable it's tinned, the shield is, and it's intended for the marine environment. We don't necessarily need this quality of wire here. But when we go back to the chart, we will see what the loss is. there's far much less loss in this, and this is kind of considered a substitute for this, which is RG8. And by the way, this is 4/10 of an inch in diameter. So is this, and so is this. You can see they're all the same diameter, but because of the construction and the type of insulation they have, I get off of there. This insulation in here, this dielectric is different in each one, so their characteristics are different. RG8 is kind of the old standard with amateur radio. And I used to be happy if I could get RG8 and use it. But each one of these has 50 ohms impedance.
Even the RG58?
All of them have 50 ohms impedance, correct? The impedance, by the way, the impedance has to do with the outside diameter of the inside conductor and the inside diameter of the outside conductor. I hope you followed that. So this is RG8. This is, I think this is this 213? Oh, this is RG8U low loss, which is one of those that was listed on our saying, and the inner conductor is slightly different. And you can see this is tinned wire. You can see how it's silver along here that's tinned. And that holds, by the way, that holds up better here on the coast than copper wire, which you can see the copper color here. It does not corrode nearly as easy. Is this 213?
213.
Right hand with the, oh, maybe.
No, I found it right here. That's really hard to read. Anyway, it says RG 213/U. Now this is a little better quality than RG8, and it gives a little bit better characteristics. But this uses the copper outer conductor. And that's really as far, whoops, that's as far as I want to go tonight with these different kinds of cables.
Do they cost about the same?
No. There's a big cost difference between all of these.
Oh, Joe,
Yes.
you might want to mention, just as long as you're showing these different types of cables, one of the other really key things, especially to those that live on the coast, is that insulator inside. If it's foam, it'll suck up water and it'll really give you problems over its short life, as opposed to if it's a Teflon insulator between the center conductor and the braid.
That is true. And one of the ways is you want to make sure that after you've made a connection outside, that you have made it waterproof. You can use shrink tubing or you can use self-amalgamating tape to put over the connection, which will help keep water out. We also have hopefully, actually, here's a little of each. This
I use stuff on
is
the 2-meter 440 antenna.
I'm sorry, what?
Oh, that stuff called stuff.
Stuff called stuff.
Is this stuff?
It's
That's
similar.
stuff.
Just you
Yes,
shoot it
it
into the
is.
connection and tighten it up.
Right here, it says STUF, stuff.
That's the stuff.
Now, dielectric waterproofing filler with Teflon. It does not affect your radio signal. But when you put it in,
What is it, a
this is,
gel?
by the way, folks, we're getting way off track.
Is somebody chewing something? Because it's making me hungry.
Yeah, I don't know. Here's a PL 259. If you take this stuff and you just put a little bead around here, when you shove it into place, it spreads out and it keeps water from going into this point here. So
So
you,
it's like caulk.
yeah, it's like a caulking, but it does not seal.
Yeah, okay.
It stays soft. And then once you've done that, then you can take this stuff, which is self-amalgamating tape. When you wrap it around here, but you take the paper off, and I'm not going to do that because I don't want this tape to stick to itself. Once you start wrapping it, it sticks to itself and it makes a great seal. And so that helps keep this from doing that. I personally use shrink tubing, which you can get shrink tubing that has glue inside. When you heat it, the glue melts, and when it seals, it fills the whole area here with glue. And that really keeps the water out. I used to do that on boats all the time. Now, can we move on? Good.
So, well, one last question maybe?
Go ahead.
So is there a rule of thumb? Like, so use RG58 if your distance is 25 feet. Use one of these other things if your distance is 100 feet. I mean, is there any kind of thing like that we can memorize rather than go and look up that table all the time?
Would you take a look at the table again for just a second, and I'll show you.
Yeah, Scott, hang on for just a second. Yes, I will do that. In fact,
Well, I'm using LMR 400 on everything for the satellite antennas and all of that. And I'm using RG 142 inside for all the jumpers because the LMR 400 is so thick and hard to move.
now, why are you using that? So why are you so intense on doing that?
One, two.
That was Don, right? Don, then you made that statement. Why are you insisting on using the LMR 400?
Because it's low loss for the satellite frequencies and it's low loss for everything.
Yeah, it is.
Correct.
Look at that.
Yeah, now
And
look
the
at
LMR
here. Here's LMR 400. By the way, it's the same size as RG8 and RG 218. Those it's all the same size. But at 150 megahertz, 100 feet is only 1.5 dB, which is,
That could be overkill for certain applications, couldn't it?
yeah, absolutely. But that's why, Don, that's why I asked you to explain why you're using that.
Well, that's what was recommended to me, and it's a good low loss, and it wasn't. I mean, it's a little bit more than RG8 or RG8X, but to me, it's worth it. And I use the LMR 400 Flex on the top of the antennas, so that they could spin around. But I've got that on all of them, on the 2 meter, on the HF rig. And then, like I say, I use RG 142 because it's so small and there's very little loss on that inside because the LMR 400 is so stiff, you can't move it around very easily to get to the radios.
Yeah.
Correct. But its loss is very low. And it's got a center conductor that won't absorb water, which is also good. But there,
Right.
now, and to answer your question, if you're talking about putting a mag mount antenna on top of your vehicle. And it's just got a 10-foot cord on it. And you're hooking it up and you're running around and you're not concerned about low signals. Don't worry about it. Just use the RG58, which comes with the antenna anyway.
Yeah,
You're not going to have in 10 feet that much loss, and you're in an application where you're not very concerned about a little bit of loss. But Dawn, is that who I was just talking
Yeah,
to,
Dawn.
Dawn?
Yeah,
Sorry, Dawn, I'm Dawn is concerned because he's trying to work satellites that are literally thousands of miles away in the sky. And he's trying to and they're only putting out, I don't know, how much power do they put out, Don?
Milliwatts, not very much, and I'm only running 20 watts transmit power.
but Don,
But that's true.
how far
The
is your,
beams are,
how far is your antenna from your receiver or transmitter?
oh, maybe 40 feet.
Yeah, so if the dB loss at 100 feet is, I don't know what.
1.5
1.5,
right here.
so at 20 feet, it's gonna be 6
40.
times less, right?
Correct. 5 times less.
5 times less.
No, I've actually probably, I think they're 50-foot sections. I've got some rolled up under the deck.
No, I'm just kind of asking to understand the dynamics here.
Yeah, if it's a shorter piece, you have less loss.
Yeah.
That's
so-
why in your shack, I like to use RG8X, this here, for short cables. Because if you're only 3 foot long, it's going to have very little loss and it has no trouble handling 100 watts. And it's easy to work with. So,
So you could, oh, okay. never mind.
Also,
Sorry, I think I'm belaboring the point.
Well,
Go
and
ahead,
then I
also.
do have another comment. As far as I can't use anything like that. I've got to use at least RG8 on the coming out of the amplifier for the HF radio.
right, but you're special circumstances. Because you're working stuff that's really critical. If you're trying to work DX, if you're trying to work satellites, if you're trying to do moon bounce, every little bit of loss counts. Because a little bit of loss can cost you a contact. If you're just talking to somebody here locally, it's typically not critical. Capiche? Everybody say yes.
Yes.
Okay, good. Let's move on. Now, well, you all remember this. Power, if you double it, and this is by powers of 2. If you double it, it's 3 dB. If you double it twice, that's 2 to the second.
4.
That's 4 times. If you double it 3 times, that's 2 to the third, which is 8 times. That's 9 dB. And if you do it 10 times, that's 10 dB. And that's in power. And that directly relates to this. And I will show you here shortly how that works. Now, this is my signal generator, except this is something I got off the internet. Notice this here, this wheel. This is how you set the output voltage of this signal generator. Now notice this right here. It says dBm. That's decibels from, oh boy, am I putting you guys to sleep. dBm is 0 dBm is 1 milliwatt. We're using a reference here for this. And then this scale here, the inside scale is in microvolts.
I mean, could you make this any more complicated?
Yes, I could. And I want you to know that Fred, if you remember him from the beginning of the class, the engineer,
Yeah.
he came over and tried to explain this to me mathematically. I almost got it. I got some of what he was teaching and I learned a lot more, but I had a hard time grasping it. But if you're going to be, and this is another check that I want to teach you people how to do. By turning this knob here, you lower the signal output and you can go down here. This is, by the way, this scale from here down is microvolts. 5 microvolts, 2, 1, 0.5 microvolts, 0.2 microvolts, 0.1, all the way down to 0.01 microvolts. And I've worked with receivers that could still hear less than 0.01 microvolts. They're extremely sensitive. But that's in reference minus 0 dBm. If you go around here, this is 0 dBm. That's 1 milliwatt across 50 ohms. Actually, it could be across anything, but in this case, it's across 50 ohms. That's just a little over 0.2 volts RMS. This is actual voltage in RMS. If you go to plus 30, that's 10, 20 plus 30 dBm, that's 1 volt. I mean, excuse me, 1 watt. You go to 10 watts, it's plus 40. If you go to 100 watts, it's plus 40 dBm. A milliwatt is the reference. That's 6 dB. Notice it's down to S7, I mean S8. Can you see that? Now, 6 dB in voltage is the same as 3 dB in power. So if you cut your signal from 50 watts down to, I mean, from 100 watts down to 50 watts, you lose 1 S unit.
So why are we using, oh, this is where we just had the convention, right? This S unit. I mean, why don't we just stay with dBs and? I mean, this is.
Just. You are way overthinking this.
I'm trying to make sense of all these things. Seems like we always seem to have multiple terms for the same concept.
Oh, that's true. The point is, and well, I guess I get lost in the details. The point I'm trying to make here is, if you go from a 100-watt barefoot transmitter down to a QRP transmitter, which is 5 watts, that is how much you will lose. 4.3 S units. You will go from an extremely strong signal at S9, and Scott will confirm this. He would be perfectly happy to get an S5 signal.
And that's because we lowered the watts.
The watts of the
Significantly.
transmitter,
Yeah.
a lot.
significantly.
And the point is if you,
1 minute.
the point is, if you want to go to QRP, which many people do, And especially in emergency communications, when you're running on a battery that has no way to get recharged. By going down to 5 watts, that's a whale of a lot less current than what you will draw if you're running 100 watts. Because if you're drawing 100 watts, that's almost 20 amps. And if you're running a 100 amp hour battery, that means if you're transmitting nonstop CW for 5 hours, your battery will be totally dead. If you drop down to 5 watts, and I don't know what that draws, very, very little, that battery will last many times longer. And most of the time you should be able to get away with it. You might kick up to 50 to 100 watts to get communications established. Once you got it, drop it down. And most likely the guy's going to still be able to hear you. So
on our radio, we must have a dial or a setting to control the watts. Is that correct?
yes,
On a handheld, you don't have that. You just have a maximum of 5 watts.
yeah, no, that's not true. Your radio usually has 3 settings: a low, medium, and high. And there's usually there's a button on it for power.
Oh, I see. Okay.
And you can rotate through those 3 different powers. Some of them have 4, some of them go down to milliwatts. And I asked everybody to start reading in the manual, because we've hit a point where we're going to be using that information. And some of what we're going to talk about is fairly advanced. So those of you who are working on your technician, just listen and try to learn. You who are going to get your amateur extra, pay close attention, because we're going to start talking about some details. But I will be talking about simple stuff first, and then we will be talking about time constants, which is something you should have read. So let's take a break. Okay, back to capacitors. Can anybody do this from heart yet?
What are they?
Yeah, what do they do? They're storage devices.
They
They're-
store energy
They're filters.
without creating heat.
They block DC. They keep DC from passing through. And they pass AC, and they're used as a timer. And one of the things we'll be talking about in detail tonight is the use of a capacitor as a timer. So let's talk about DC, AC, and frequency. Now, this is a sine wave. If you look here, you can see it starts out at 0 volts. And this is like my oscilloscope screen. Across here is time, and up and down here is voltage. This is 0 volts. This is plus voltage, and this is minus voltage. So we start out and we go up, and then we come down, and then we go down, and we come back up again. That's AC. So then earlier we were talking about voltage peak to peak, right? Now we can look at a signal from a single sideband transmitter, and although it's not a sine wave, it has peak from here to here, and it has peak to peak from here to here. So, and we can take that and come up with the volts RMS value, which is a given at 0.707. And as I told you once before, if I could remember how to do calculus, I could tell you how to get there. I can't anymore. So moving on, here again, the same thing. Now, volt average, I hope sometime I learn why they even bother to put that in there, but volts RMS, peak and peak to peak. Let's just start getting these concepts. And then here is a sine wave going up, down, okay, around 0. And then if you converted that to DC, which is coming straight across here, all the area that's underneath in the blue, if you put it all together, it would come out just like this as DC. So the power of this is the same as the power of that.
Mhm,
And thank you.
mhm.
If Ann's agreeing, you've all got it, right? Hopefully. So we look at frequency, and very shortly here, I'm going to show you this on my oscilloscope and let you listen to it. And I hope that Zoom does not cut out the tone. But it has special filters that do some strange things. But here's a high frequency. And notice the time between each peak is much shorter than the medium frequency and much, much shorter than a very low frequency. So here we go again, short wavelength from peak to peak. And a long wavelength from peak to peak. High frequency, short wavelength, low frequency, long wavelength. So let's demo.
All right.
All right. Now, here's a low frequency, and we can see the time from here to here to here, which corresponds to wavelength. Now, it doesn't matter if it's sound or HF or VHF or microwave. As these get closer together, as the frequency goes up, they get closer together. The wavelength, which is represented by each one of these peaks, gets shorter.
Yep.
Oh, Scott, this was a great find.
Yeah, it was.
Can you guys hear that?
Oh, yeah.
Oh yeah, it's very annoying. But you can see this very short wavelength. And then we go on down. And then we can go on down from there. Okay, now I'm going to kill the sound. Notice this red line right here. Now I did this very much on purpose. This is 0 volts right here. From here to here is 20 volts peak to peak. From this point to this point is 20 volts. Peak to peak. From this line, which is 0, up to this point here, it's 10 volts peak. This line right here is 7.07 volts. So if this is a DC line, direct current, you can see it from 0, it goes up and it just stays above 0. Now this line could wiggle, but as long as it stays above this line, it's DC, direct current. It's only going one direction. AC is when a signal goes back and forth across 0 volts. So that's the difference between DC and AC, which is here. Capiche?
Capiche?
Yeah, all right. I am glad to hear that. Okay. Any questions?
Hey, Joe,
Yes.
remember when you said after Ann asked about the sound, and you said that was just about our perception?
Yes.
Well, that is bothering me. Or is that not worth thinking about at
Well,
this point?
Oh, here, let me,
Let me go a step further with that. It's more to do with the frequency and your hearing, I think, than it is perception. I think what Joe's trying to say is the voltage is the same at both the lower frequency and the upper frequency, but your hearing is not the same. That makes sense.
Yeah, you can have a high frequency sound that can't be heard by humans.
Sure. So I think more than perception, it's your hearing that responds that way and how you interpret that signal.
Correct. Yeah, it has nothing to do with the actual signal. It's your hearing perception, and we all hear it a little bit differently, but the ear is more sensitive to those higher frequencies. In amateur radio, and this is an important point, microphones are set up to transmit from about 400 hertz to 3,000 hertz, 3,000 cycles per second, which is the voice range. And when telephones first got put in, they narrowed the voice of the telephone to that. So if somebody was back there playing a flute, you probably wouldn't even be able to hear it because it was a higher frequency than what would go through.
Joe,
Yes.
can you change your audio setting? Can you click on that thing and put the sound for musicians off again? Because we're getting all the background noise now.
Yeah, yep,
Oh,
yep.
oh, now how's that?
Good.
Oh, okay, good. I'm glad I've got you guys to keep me straight. In amateur radio, you do not really want to have a microphone that's flat from 50 hertz to 20 kilohertz. And if your radio is trying to transmit that, it won't do it because it's got a limited bandwidth of about 400 hertz to 3 kilohertz. And if you're actually trying to make a really clean signal, you'll drop that down to 2,400 hertz or 2,200 hertz. And some people even drop it down on the receive side down to 1,800 hertz. So that you get rid of all the excess noise that's coming in at you. This high frequency stuff that just interferes with what you're trying to hear. And the microphones, in order to get the punch, emphasizes the higher frequencies of your voice. And people can hear that better than talking way down here. Because this doesn't go through very well. But this does. And that's something that when you're selecting,
So women should have an advantage here, right?
they absolutely do. And when you get on there with this nice feminine voice and say this is a YL, you will get lots of people giving you a call because even though we've actually, it's a good thing, we've got quite a few people now that are women, but when I was young, there were very few women in this hobby, and thank God that's changed because it's wonderful to have you all here. In fact, women have made wonderful contributions to the hobby. And that makes me think of that one actress, Hedy Lamarr.
Eddie Lamar, yes.
Hedy Lamarr, that woman was absolutely brilliant. And the things that our phones work on through, Daron, can you help me in what kind of transmission that is? My mind's going blank.
Well, our phones don't really use it. Wi-Fi use the frequency hopping extensively. The phones are a little more of a dedicated channel, channelization, but all the Wi-Fi stuff is, and all that data is done with a lot of frequency hopping, where the frequency jumps between different channels, and that was a program or a design that she engineered.
Yeah, and that was during World War II, in the 1940s. And unfortunately, she died poor, and the military put her stuff to great use. So moving on to capacitors. Darren, what was that you just put up?
Oh, I just sent a link to the Wikipedia page about Hedy Lamarr.
Oh, oh, okay.
If anybody wanted to go look it up and read, it's absolutely amazing information. Brilliant lady.
Yeah. Yeah, kind of one of my heroes. All right, back to capacitors. We're all familiar with this. Essentially, there are two plates, metal plates with a dielectric in between. And the dielectric can be air, vacuum, paper, and all kinds of other stuff. Like in this illustration here, we have all kinds of capacitors. These are electrolytic capacitors. They're usually have a high level of capacitance, but that's done because they use a chemical in them. And once they're polarized, they have higher capacitance. Here's a suppressor capacitor. These are used on AC inputs and equipment to keep noise from coming in and out of the receiver or the transceiver. These are chip capacitors. They're little tiny things. If you remember, I showed you last week a chip capacitor and it looked like somebody dropped a piece of pepper on the paper. Tiny, tiny thing. Ceramic capacitor, polyester, polypropylene, polystyrene. These are all insulators that are used. They all have specific characteristics. I couldn't even explain most of them to you, but they're useful in different applications. So moving on, this is a capacitor.
Oh, no, get back. Sorry,
Heel,
Problem.
I have an intruder.
heel.
All right, let's go to the camera. So I'm just going to try another attempt to explain how a capacitor works. And basically, there's a capacitor. Now, we're going to hook a battery up to this. Okay, for my smart students, what side is this?
Negative.
Nope.
No.
Yeah, a 50-50 chance.
Yeah.
Okay, this is the positive side. What side is this? Negative. Okay. Yeah, when I first did my, oh, I don't have it here. My little thing with all the electrons on the rod, the little blue pills. I had that backwards. But what happens here is we've got a negative charge on this side and positive charge over here. Here we got electrons, right? Here we got holes. So these electrons, because these are holes on this side, they will attract the electrons over here. And so the electrons will move up and they will start forming on this side of the capacitor. These electrons will force the electrons that are here to go this direction. So if you got an electron, they're going to head over to the positive, to the holes. So what you end up is with a bunch of holes on this side and a bunch of electrons on this side. This is negative and this is positive. This creates a electrostatic field that goes across there. But if you understand electricity at all, there's no way for DC to circulate here. What's going to be the current through this circuit for DC?
0.707.
There you go.
I don't know.
F.
Zero.
I don't,
Zero. DC cannot, remember, it's a DC blocker.
yes, yes, I know, yes, I remember now.
It's a DC blocker. So DC cannot pass through a capacitor. Now,
But how does the DC even get into that circuit?
well, the battery is an electromotive force. It's a force. It's trying to push electrons this direction, and it's trying to push holes this way or attract electrons this direction.
Mhm.
So as soon as you put the capacitor in, here's the plates, the electrons flow this direction
Mhm.
because these are holes over here. So they're attracted to them. When they get over here, they also help shove the electrons that are on this direction to come over to the battery.
So we
When-
charge it.
Say again,
We charge it. We charge the capacitor up that way.
that is correct. If we look at this in time, if we have a battery, a switch, and a capacitor like this, if the switch is open, this is 0 time here, right? And this is 0 volts. We'll say this is 5 volts and this is 5 volts up here.
I
That's a-
can't see that.
That's a 3-volt battery, Joe.
There we go.
There now, is it a 5-volt battery?
No, you need another, well, it's a 3-volt battery. Each small and large segment is one cell.
Well, correct, but it can also be used generically for any number.
Sure. Got it.
This is a generic one.
Okay.
Okay, at the instant that you close this switch, current then can flow through this circuit. And what happens is it starts out at 0 volts and the capacitor starts charging. So after X amount of time, the capacitor will have gone from this state up to this voltage. And the instant you close this, if there's no resistance in here, it would be extremely high current. Because there's nothing stopping the current from forming here and pushing electrons off of here. But there is a little bit of resistance inside the battery or the power supply, and there's a little bit of resistance in the leads, which help do that. But as time passes, goes on, it continues to climb. As it gets closer to the 5 volts, which is over here, the rise time slows, and eventually it comes up here and it reaches 5 volts.
So is the time it takes to do that important or?
Yes. This is the point of tonight's class. Did you read your manual tonight?
No,
Oh,
sorry, I know, I'm behind.
yeah, you're behind. This is, we are going to be discussing time constants. And resistance time of the capacitor is equal to R times C. Darren, did you end up with a 100 microfarad capacitor in your thing tonight?
Right. I have some.
Oh, good. 100 microfarad. Did you come up with a resistor?
I got to show you, Joe. Hang on just a second here.
What do you got? A whole bunch of them?
Well, that's not the right camera. This got this on Amazon for like $18. It's just a little binder, and it's got all these values. You just comb through and pick whatever value you want.
Oh, so you have not.
Take the package out, and whatever value you want, Joe, I will have.
Gotcha.
Oh, look, he's got toys.
It's
How
cool.
much was that kit?
Oh, it's $15 or $18, I think, or something, but they're high tolerance and it's a,
Oh, look at,
So-
oh yeah, look at the scale.
yeah, the chart was nice. It's a nice little way of having them, so they're easy to find.
Okay. Well, I tell you what, I did a little arithmetic. Start with the 50K or something about 50Ks.
47K probably.
Yeah.
I'll find it here.
Here, I'm gonna call it 50K though.
Okay.
The instructions to this say the time constant is equal to RC, but if R is in meg ohms and C is in microfarads, then you get the correct thing. So if you got 50K, that would be 0.05 ohms, meg ohms, and this would be 100 farad. So if you take 100 multiplied by 0.05, that comes 500. Move the decimal point over 2 places. So that is 5 seconds. I actually figured this out today, Daron.
Nice.
So anyway, if we look at our curve here, and we have I'm just going to kind of guess. There are, I've got some pictures that are actual nicely done, but if this is 5 seconds, 10, 15, 20, 25, 5 seconds comes to this point right here, which should be 0.62, right? Somebody know?
No,
No.
I don't know.
I think it's either 0.62 or 0.6. Yeah, I think it's 0.62 volts. And then this one will be a value here. This one will be a little higher. And this one will be a little higher than that. Each one getting narrow. When you hit 5, 1, 2, 3, 4, 5, that is considered to be a fully charged battery. I mean, not battery, a fully charged capacitor.
So is the 5 divisions related to the 5 seconds or?
Yeah, this is 5 seconds, 10 seconds, 15 seconds,
Right, but
20 seconds, 25 seconds.
so, but you said when you get to the 5th.
Yeah,
increment,
this is
So say.
this is T1, T2, T3, T4, and T5.
Right,
Time constant.
Oh, so it's 25 seconds, not 5 seconds?
so at 25 seconds, it's fully charged.
Yes, for this combination here.
Right, but if the 5 seconds had been 14 seconds, then it would be 5 times
It'd be-
14.
Correct. Yeah, and let's get away from this. Remember how we figured out what the value was? If you got capacitors in parallel, you treat it as if they're resistors in series. You just add them up. C1 plus C2 plus C3. And it's that simple. If you have capacitors in series, you treat it as if they're resistors in parallel. It's just the opposite of what resistors are. Then we come to this constant. This is in your manual. This very statement right here. Here is the thing that I drew, except that now this one has a resistor in it. This is the resistor that we're talking about. And for now, we're going to try, what did you find, Darren? 47K or 50K?
Yeah, 47K, but that's an inductor you have there, not a capacitor. So that'll be the next traffic cop of radio. That'll be the block
Yeah,
DC pass AC.
I'm sorry, that's going to be next week or the week after.
Yeah, sorry.
I
I just
grabbed it.
wanted to point that out.
Oh, thank you. Yeah, this should be a capacitor. I'm sorry, it should come up, have a plate, have another plate, and then go like this. And, oops.
We can fix it.
Yeah. Anyway, time constants. The book does both the capacitors and the inductors at the same time. I want to treat them separately. So anyway, moving on, here are the time constants. It's 63.2 volts. The one time constant, here's T1, T2, T3, T4, and T5. In our example of 50,000 ohms, T is 5 seconds. So this would be 5 seconds, 10 seconds, 15, 20, and then 25 seconds, which at that point they would consider it to be at full voltage, which for us with our equipment is going to be 5 volts. But if you see how the charge and see how it is not linear, linear would go straight up like this. Ours does not do that. It's exponential. So it starts charging up very quick. And then it charges more, but the charge rate is slowing. And this gets slower. This is 4 time constants. And it's 98.2% of the voltage that you would have. If you had 100 volts, that would be 98.2 volts. Now, also, you can discharge the capacitor if instead of having it up to if you had charged it up and then you went through a resistor and you coupled that resistor to ground, it would discharge the capacitor. And you could start at, and we could call this 100 volts or we could call it 5 volts. But when it drops to 36.8 volts, that's one time constant. And you notice that if you take this and this, they add up to 100%. So they're just the opposite. But now for everybody that's taking your test, this value and this value, you need to know. So if you know this one, you will know this one, and it's on the test. Got it?
What is it called? So
That's a time.
the time constant, oh, it's just T1 then is the time constant.
Correct.
Okay, okay.
T1, right. And you have this both for capacitors and inductors. In capacitors, we can slow it way down and watch what happens. On inductors, we don't have any inductors that big. We'd have to use an oscilloscope to observe what's going on. But so now moving to the next slide. Darren,
What?
you're on.
Well, Joe, we're kind of shooting from the hip here. We'll see. We have a 47K resistor. So we have our 47K resistor. And help me out. How do you want to build this, Joe? We want to use this to charge our capacitor.
you've got a 5-volt supply, right?
Correct.
Yeah, and you'll need to put the resistor and the capacitor in series. Of course, that's
Okay.
electrolytic, so you'll need to make sure you have the polarity correct.
So what we're going to do is we're going to take our 5 volts.
Yeah, but
Put it
don't
there.
hook the 5 volts up yet, Darren,
Okay.
because we want the capacitor to be discharged to begin with.
Okay. I'm just going to put my resistor in here.
So-
Just the little teeny resistor, right?
So to discharge a capacitor, you need a resistor.
No, you can just short it.
Okay, that's what I was wondering. Yeah.
Now, oh,
Just taking-
see what he,
Taking some metal here and shorting the 2 leads together.
Okay.
So we'll take the negative lead and we'll put it down at the bottom here. No, it's not going to work to build this. Sorry. Let's do that.
yeah, point to, we can't quite see. Yeah, there's where you're going to hook up the positive.
So there's my resistor. It's hooked to the positive lead of the capacitor. And then ground is down here on the capacitor. So we have a couple jumpers to put in place, right, Joe, to make this work?
Yeah, go ahead and put in your ground.
Okay, well, that means I got to find another jumper. Hang on just a second. Sorry, didn't have that sitting out there.
Well, you could have put the negative end in where the jumper is already, you know.
Okay, Joe. Let's do, how about this? Okay, so now we just changed this a little bit. So the negative side of the capacitor is in the column here with the ground,
Oh,
right?
there you go.
We jump over here and I missed it by 1. Then we're connected to the resistor and we'll apply plus 5 volts to this side of the resistor and power will go through the resistor and charge up the capacitor, right?
Correct.
Okay, do you want to
And now-
meter that as we do it?
Yeah, put it across the capacitor.
Okay. We'll go for DC voltage here because that's my favorite kind.
You mean you don't like 120 volts AC?
Not particularly.
Well, the reason I don't have any hair is because I got across it one time and couldn't get loose.
Yeah, that'll do it.
Okay.
All right, so we have no
Zero
voltage
volts.
there. No voltage. We're going to take, let's put a little power to this. So our LED is on. We have power to our voltage regulator.
So you
This
got
is plus
5
5
volts.
volts.
Now, before you do that, Darren, the first point will be 0.632 or 63.2% of 5 volts. Have you figured out what that is?
No.
Okay, hang on just a second.
And that's going to happen in 5 seconds?
3 seconds.
5.
3 seconds. 5 seconds.
5 seconds.
3 something.
3 volts. 3 something.
Yeah, wait a minute. 5 times 0.632 equals 3.16 volts. So
I should have grabbed an analog meter.
3.16 volts. And if you do 2 time constants, I don't I don't have the screen in front of me, so I can't tell what. Does anybody? Does it? Oh, wait a minute. Where's my book? We'll do 2 time constants, and then I think we'll be about out of time.
Constantly.
Oh, the second one is 86.5%. So 5 times 0.865 equals 4.32
seconds.
Volts.
volts.
2 volts. I mean.
Okay, so the first time constant will be, well, approximately 1.16 volts.
Okay,
It's a little bit different because this is I'm sorry. Yeah, it's a 47K resistor, so it'll be
right.
a little bit shorter time.
Okay, I'm just gonna, before we start, we're just gonna make sure we have 5 volts over here.
Yeah, close enough.
Pretty darn close. All right, you ready to count, Joe?
Oh,
Yeah.
1 second.
Here we
2
go.
seconds.
wait a minute, wait a minute. No,
1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000.
it just passed 3.168, and there goes 4.3, so that's 2 time constant. And notice how it's slowing down,
Will it
and that's
stop
how
at
a
5?
capacitor acts.
So will it stop at 5?
Yeah,
Whatever the supply voltage is,
Yeah.
minus that little bit of resistance.
And
Okay.
so of what use do we make this? I mean,
this is a taper.
Now take your voltage off.
Wait, Scott, you're not in charge. I have to wait for
Okay.
Joe.
All right.
Okay, there goes our 5 volts.
yeah.
Now go-
Now we're gonna go back down.
Yeah, it's discharging through the meter. And you can see it's going very slow. If you grounded you shorted it.
Yeah, I shorted it.
On purpose.
Yeah, that definitely will discharge capacitor.
Let's do this part again. So before we did this with integrated circuits and all kinds of fancy stuff, this is how we did timing.
Yeah. Now, here, I'll just give you an example. If you were going to be transmitting, well, let's say moon bounce, and you're using a radio to drive a great big amplifier. When you go to speak, you have relays that are typically out by the antenna or in some other location. If you speak in your barefoot radio, transmits before the amplifier gets switched over, it can damage the radio, the barefoot radio, because it doesn't have a proper load. So what you do is you put in one of these timers. When you click the transmit, it keeps the barefoot radio from transmitting for X amount of time to allow the amplifier to get switched over and ready to take the power. Did that make sense, Daron?
Yes, sir. We could also make this to a 10-minute timer. You know, we could put a bigger resistor in there and make it a light come on at 10 minutes to remind you to identify. All kinds of timing things can be done this way.
Yeah. Or you could have it set so that the time would flash when the repeater is about ready to cut you off.
That's not fair. We like to keep that random and kind of vary that around. But yes, absolutely.
So, so this circuit board that Daron's working on, you would attach that to your radio somehow?
You would put a little box in between your microphone and the radio.
That would do this function.
That would do this function, and it would hold off the push to talk for X amount of time while it gave the push to talk to the big amplifier first.
Joe,
Yes.
some transmitters have a transmit delay built in. Or you
That
can-
would be
you can-
wonderful.
Yeah, you can set it up to where it delays the transmission per millisecond.
Yeah, what is a typical delay? I was thinking about that today.
Well, I don't have mine on. I think it's like 32 milliseconds or something like that.
Yeah,
It gives giving the relay time to click in, I guess.
yeah, yeah. Well, very good, folks, we're out of time. So, this was fun tonight. Did everybody learn something?
Yep.
Thank you,
Absolutely.
Darren.
Absolutely.
Thank you.
Yeah, and Darren, you're always giving great displays. Thank you. Well,
Well,
God
it's
bless
just-
you all. Oh, Lord, I forgot you. Anyway, thank you for making this turn out so well. Have a good night, everybody. And, oh,
Thank you,
and
Joe.
remember-
Thank you. Good teamwork.
Yeah, remember, no class, April 13th.
What?
Spring break. Oh, you were gone, see? You got away from your radio. I am going to Eastern Oregon to go to celebration of life for the co-founder of Maritime Ministries. He and his wife and Janet and I started Maritime Ministries together.
Okay. And
And
that's April 13. I think the week after that, I'll start my trip to Scotland. I'm not getting up at 1:30 in the morning to visit with you. So,
oh,
come
Oh,
well, I might, I don't know, but I don't think so.
It'll be cold and dreary.
Yes, it's all right. They have whiskey
It keeps you warm.
A good thing too.
and I can wear my kilt, so it'll all work out.
And your long johns.
Yeah, probably so.
well, it looks like half the people are gone already. So,
Joe, thank you
God
very
bless
much. That was
everybody.
awesome.
Well, have a good time on your trip.
Thank you.
Yeah, well, we've got what, 2 more weeks left?
Oh, yeah, we'll make it.
Just a minute, Bobcat.
Yeah.
Okay, guys, have a great evening.
Good to see you, Don.
have a good one.
Good night, all.
Bye, you guys.